Time dilation is a phenomenon predicted by Einstein's theory of special relativity. It states that as an object goes faster, it experiences time slower in relative to a bystander. In 1971, an experiment to observe time dilation was set up using two synchronized atomic clocks. While one remained stationary, the other flew around the world. Once reunited, the atomic clocks were out of sync by 40 nanoseconds. Sergei Krikalev holds the world record in time dilation. He spent 803 days orbiting the Earth at 27,580 kilometers an hour. And because of this, it is estimated that he has aged 20 milliseconds less than people on Earth. So how do we explain how this works? One strange behavior of light is that no matter what frame of reference you're in, no matter how you're moving through the universe, you'll always measure the speed of light in a vacuum to be the same. This phenomenon has been proven by the Michelson-Morley experiment, which showed that light did not permeate through an ether. If a spacecraft traveling at 87% the speed of light turned on a flashlight, the light would be traveling at 1c. The speed of a light source doesn't push it faster. But this time, if we take a measurement of the speed of light from the spacecraft's reference frame, we will see that the speed of light is no longer c, but half of c. But as we saw earlier, the speed of light is always a constant, no matter the reference frame. To make our equation true, the only other variable that we can manipulate is time. Now if you look at it with clocks to show how each reference frame experiences time, we see that the light takes the same amount of time to travel the same distance relative to the spacecraft. Now that we understand the concept of time dilation, let's quantify it. This is Einstein's equation that predicts how the rate of time is affected by velocity. To understand how this equation was derived, we can set up a thought experiment. Consider a light clock where a photon of light bounces between two mirrors. As the light clock's velocity increases, the distance that the photon must travel inside the clock is increased, and so each tick of time is longer. But to an observer traveling with the light clock, the path that the photon takes is a straight line. Because the speed of light is the same for all reference frames, the observer traveling with it will see that each tick will take the same time as a stationary light clock. By comparing the distance that the photon travels to bounce between the two mirrors in each reference frame, we can understand how the different reference frames experience time. This distance can be calculated using the Pythagorean theorem, and by simplifying this equation, we arrive at Einstein's original equation.